When we talk to somebody about three dimensions or 3D, what we usually mean is R3. Mathematically, but still quite informally, what that means is that I can represent any point in space by an x-coordinate, a y-coordinate, and a z-coordinate. That's three dimensions, one in the x direction, one in the y direction, and one in the z direction. You may or may not have seen this yet, but we could also represent this in what's called cylindrical coordinates. And we would do that by going out a certain radius, around a certain angle, and up z. But that's still three dimensions. Even spherical coordinates. Many of you may not have seen these yet, so don't panic. But the idea here is that we would go out a certain radius, around a certain angle, and then down a certain angle from the z-axis. And that would give us a point. Also, it's hard to draw that actually. That would give us a point in 3 space as well. So all of these are in R3. They all have 3 dimensions, and sometimes we call those dimensions x, y, and z. Sometimes we call them rho, phi, and theta. It depends on which particular coordinate system you're working with. But 3 dimensions are 3. Fortunately for us, when we talk about the dimension of a vector space, when it comes to the space being Rn, that vector space is going to have n dimensions as well. So we talk about n-dimensional vector space being a dimension of Rn is n. And the reason for that is that we have n vectors. In R3, I would say I had the x vector or the I vector, the j vector, which is the y vector, and the k vector, which is the z vector, right? I have 3 directional vectors that together, and although collectively without any additional help, those 3 vectors make up all of R3, or can be used to make up all of R3. And whether I'm using x, y, and z, or r for radius, theta for that angle, and then z, depending on which system I'm using, I'm going to use different letters and I'm going to be going in different directions, but I still have 3 directions I'm going in. So that's what I mean by three-dimensional. Regardless of which case I'm looking at, I can always say that a basis, in fact, I'm going to back up and say because I'm going to be talking about the standard basis for R3 is the 3 vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. In R3, or in Rn for that matter, it's easy to talk about the dimension of the space because the number of components of the vectors match the number of the vectors. So what we say, and the way we write this, is that the dimension, I'll write it out first, and what I'm doing here is defining this word in this particular context. The dimension of Rn is n. And our abbreviation for that is dim of whatever space I'm working with. In this case, it's Rn equals whatever that dimension is. Oh, that should be an m, not an n. Dim is just short for dimension. So this new notation just means what is the dimension of the space we're talking about. And the space we're talking about goes in the parentheses here. It's a little bit like an argument. It's a little bit like function notation. Now that's the standard basis for R3, but any basis for R3 is going to have 3 vectors in it because that's what we need to span R3, and we need them to be linearly independent to call it a basis. But the minimum number of vectors we need to call it a basis is 3 in the case of R3, or n in the case of Rn. Let's say, though, for example, that we have 3 vectors, 1, 0, 0, 0, 1, 0, and 2, negative 3, 0. And I want to find the dimension of, I've made that a matrix. What I really meant to do here was to make it a collection of 3 vectors. And what I'd like to do is find the dimension of the space spanned by those three vectors. This is actually very close to the exercise we did at the very beginning of the last video, or maybe it was the one before that. It harks back to the participation activity in section 4.3, activity 4.3.2 about minimal spanning sets. They give us a different third vector in this case, but I'm going to use, I'm using one that I came up with myself here. So what I want to do here is figure out the dimension of the space spanned by this collection of vectors. So what I'm really looking for is the dimension of a subspace, and that subspace is the span of whatever my set of vectors is called. Let's go ahead and give it a name. I'll just call it S. That's been pretty consistent. And so I'm looking here for the dimension of the span of S. Now, S might turn out to span all of R3, but it turns out it's only going to span R2, which you might be able to tell just by looking at, but we're going to go through the process again of figuring that out. I'll start by putting this collection of vectors into a matrix. And again, you don't, strictly speaking, need to do this step, but I do want to remind you that's kind of what's happening here. You could theoretically skip this step because you're really looking at that here. It's just got these extra sort of vector cages around the vectors. Right here, they've just been turned loose into a big pen, but they're maintaining their structure. I still have these three vectors. They're just columns of a matrix now. What I need to do to figure out what a basis is for this collection of vectors is to reduce this matrix, the one I made from the vectors, into reduced echelon form. And then I can look at the pivot columns and tell you which are the corresponding vectors in the original collection of vectors. Well, as it happens, because this was a very early example, our two pivot columns are already visible. We don't have to do any vector manipulation or any matrix manipulation to find those two pivot columns because it's already in reduced echelon form. So the two vectors 1, 0, 0 and 0, 1, 0 form a basis of this set of vectors. And remember, we said back in the last video when we were talking about this, we were talking about finding a basis, that what we have found is a basis for the subspace spanned by S, right? This is in R2, not R3. Actually, let's write it as a sentence here. This collection of vectors, a set of vectors, is a basis. And it's a basis for R2. And what we have now is another way to think about that, another way to define that, and that is to say that the dimension of the set we called S is equal to 2. And that's really what that means. And the formal definition of dimension is that the numerical value for the dimension of a subspace is the number of vectors in a basis for that subspace. Now, this is not necessarily the only basis for our space S, but it doesn't matter whether I find this basis or another basis, it's only ever going to have two vectors in it. So no matter which basis I find, all I have to do is count the vectors and I'll have the dimension of the space that I'm working with. It is possible to have collections of vectors with an infinite number of vectors in them. So it's possible to have an infinite dimension. We're not going to be dealing with that at all in this course, so I don't want you to worry about those. Just know that it is possible. And then the other special case is the dimension of the vector space that has only the 0 vector in it. Let's call that vector space Z. And it's made up of the collection of vectors where the only vector in there is the 0 vector. Now this is not the empty set. The empty set has no vectors in it. This set has one vector in it, and regardless of what dimension you're in, that vector is the 0 vector. And what we're going to say, just going to agree, is that the dimension of that collection of vectors. The dimension of the vector, the set containing only the zero vector, the numerical value of that dimension is 0.